on to presentation time.
So, hello everyone, my name is Marie, and today I'm going to show you my solution to problem number 12, the autumn coin. So, the motion of a coin falling to the bottom of a tank filled with liquid can be remarkably similar to the fluttering and tumbling of a falling autumn leaf. And we should investigate how the motion on the coin depends on relevant parameters. So, this is what you're going to see in my presentation. First of all, let's start by defining what is fluttering and tumbling. So fluttering is this side-to-side motion, and tumbling is when the coin falls, then turns around, then falls again. So for the basic explanation, the coin is moving with some velocity v, and opposing that is the drag force. So because of the differences in pressure, there's lift force, that's the basic gravitational force, and the buoyancy force, and all of these forces create a torque. So, when we have coins with large diameters, the dissipative torque is greater. So, the motion gets stopped and the coin flutters. But when we have coins with smaller diameter, the dissipative torque is smaller and the coin is able to tumble. So, for the demonstration, these are the three types of motions that I was able to observe. So, first of all, let's start with the tumbling. So you can see that the coin falls and it turns around, falls again, and like moves and tumbles to the bottom of the tank. Next, we can look at the fluttering. So here we have a large disc and it moves from side to side. These videos are slowed down 10 times and we used 1000 FPS. So, and this is a transitional movement. So we define this like the movement between tumbling and fluttering. So it, for example, starts to tumble, but then it changes this mode and it starts to flutter, or it does something else. And we were able to observe the fluttering with like large discs. So not coins, but we still investigated this. So this was my experimental setup. I had a large tank. I used an electromagnet, so I was able to release my coins very stably. I used all of these different coins and discs. And then in the problem statement, it says to use liquid, but it's really hard to fill up like a 170-liter tank with oil, for example. So I used salt to change the density of the water. So for my theory, we can write the equations that I explained before. And we're going to make a simulation. This is a very complex problem, so we're going to model it in 2D. So we're going to take the cross section of the coin, and this is an ellipse. But if we cut the coin at the end or in the middle, this A would be different of the ellipse. So we will introduce an effective A, which is basically we integrate from side to side, and this fixes this problem. And B, which is the thickness of the coin, remains constant. Then we will define some added mass 1, 1, and 2, 2, which is basically the mass of the water moving with the coin as the coin moves through the water. So you can see here, and indeed this is cited, and in the other dimension. And there's an added moment of inertia. So again, from the water moving with the coin. Then we made CFD using docile 3D experience. This is just to basically check if we can discard or the relief of the coin is negligible. Yes, it is, because if we look at the velocities, they differ only slightly, so it is completely okay to assume the coin to be smooth. So for my simulation, we can rewrite again the equations as here with the terms that I explained before. And I have a system which rotates with my coin. So we have an added fictitious force. And then this is from literature, with this being the torque from transitional movement. So when the added masses are not the same, there's added torque and dissipative torque. This is from this literature. The lift force looks complicated, but it is pretty just like the standard version of lift with the added effective A, with this being the rotational lift, which is very similar to the Magnus effect, which is basically when something like turns, it has a tendency to go upwards. And then for the drag, these two coefficients basically take into account how the coin is angled. And then we have the so all of my coefficients are, well, some of them are from literature. As you can see here, two of them were fitted because, well, we weren't able to find any like reasonable or applicable values in literature. And in the literature, they obtained them by computing a very like complicated CFD. So it is not like just from some experiments. Now, looking at my simulation, I used the fourth order Runge-Kutta method, and it's like amazing. I'm very happy with that I'm able to observe all the three types of motions that I was able to see in my experiments too. So the tumbling, the transitional movement, where you can see that the coin like starts to tumble but then goes to the other side, and the fluttering. So to compare, let's start with the different modes. So we can see that the different modes do depend on the coin diameter, as I explained in the basic explanation. So this is the tumbling, the transitional movement, and the fluttering, with the most of like the coins in the fluttering region being the like, big discs, not my actual small coins. Then I change the density by adding, well, salt to the water, and we can see like a slight difference in the strength. Next, we are going to see, look at the average angular velocity. So here we see a very nice agreement with my simulation that the angular velocity of the coin turning, flipping, changes with diameter. This makes sense because the mode changes too. I would like to just like, clarify how this is done. This basically takes, this error bar is from like running the simulation with slightly different input parameters, like the, for example, the initial angle, and it is from like the uncertainty of measuring some of the input parameters too. Sorry. So now let's look at the average falling velocity. We can see that this doesn't depend really on the coin diameter, but in some like which cases it could. And for the falling density, well, as I said before, it is really hard to really find like different liquids, but it does have a slight decreasing trend because it's like harder for the coin to like move through the liquid. What I explained before is like all of my experiments so far were done by like having a small release, like some initial release angle. But now what I did is that I had my electromagnet like completely straight, and the coins were released from this type of position. And I noticed that this does like even like a small some like small difference in these release conditions can create difference in the like side to which the coin moves. So what basically I'm trying to say with this graph is that like changing the initial angle doesn't change the actual mode in which it like tumbles. Or for example, here it's tumbling, but it does change the side to which it goes. And here I run my simulation like 325 times as my experiment. The simulation is very light, and you can see that here it like overlaps a lot. And again, my simulation, there was like a small difference in the release angle. Because even though I used an electromagnet, it has some error because like it isn't perfect. And here were the edges of my aquarium. This is why the coins don't go further. So, as I explained before, we see some like dependence on the initial angle. So it's pretty sensitive to this. So this is why we calculated the Lyapunov exponent for all of the different modes of the motion. And we see that the Lyapunov exponent is positive. So this is one big indicator that this system is chaotic, but physically chaotic, but it's pretty small. So, so yeah, and we calculated this using the Rosenstein algorithm. I can explain further. And looking at the values, the transitional movement has the highest Lyapunov exponent. So looking at the trajectories of the movement, this is from my simulation, we can see that we change the input a little bit, and we do see pretty the difference in the motion. So, in the problem statement, they say that it can be remarkably similar to the autumn leaf, autumn coin. So if we take our equation that we had before and assume that the thickness divided by the length of the coin is much smaller than A, we can get these expressions. This is from literature. This is the non-dimensional moment of inertia, let's call it. And calculating one for the leaf and the normal coin, we can see that the values are pretty similar. So this is why we can the coin can move in a similar way. Obviously, this is simplified, but yes. So to conclude, I explained the forces my task. Then I computed a simulation that is able to predict the 3 types of motions that my experiments are able to see, which you can see in my experiments. And then I compare this to my experiments, and it matched very nice with my simulation.
Okay, thank you very much. Straight into 2 minutes of questions from the opponent.
Okay, so thank you for that amazing presentation. So firstly, have you calculated the Reynolds number?
No, but...
Oh, okay. And then for the CR and also mu1, how did you fit it?
We fitted it from our experiments.
Okay.
From
And then how do you define a transitional movement?
When it doesn't purely flutter or tumble to the bottom of my tank. So
Okay, we'll discuss it later. And then have you thought about the head tail distribution? Like I see if I drop it at the head, what is the probability that it will end up in the head?
I'm not sure what you mean by this.
We'll discuss
so
it.
we can.
Is the initial angle of the release varied in your experiment?
Well, for these, there's a small initial angle, so we can control to which side it goes.
Okay.
Just to
and then moving on, for experiments, I'm not really sure, did you release it in the water or above?
in the water.
In the water, okay.
I can show you.
And then, how many camera perspectives do you have in your experiment?
One.
You only have one, okay.
Yes, I have it from the front.
And also...
and then for the coin, I looked at the front.
Okay, so this is only, the top view is only for the distribution of
yes.
the coin. Okay, and then next, for the simulation that you have you simulated the grooves in the euro coin?
No, as I stated with computing this CFD, it is negligible. Okay. So in my simulation,
for the CFD, you simulated grooves in the euro, like inside.
The grooves in the sides it looked like this.
Okay, so, and then can you also I assume that
because sometimes
and then have you verified that there won't be the rotation of the coin in your experiment? Well,
my experiments looked like it went to the side, so I do neglect any rotation like this.
Like rotation along.
You can see it goes like.
Okay, thank you. That is time for questions. You now have preparation time. Reporter can sit down for a bit.
賽係自己本地定係海外嘅？
HK 咯，
香港自己。
都唔知。
咁你係講緊頒獎嗰刻啦，定係比賽中途先？
科目頒獎嗰刻或者影相中，全部都有嘅。跟住 Q 部分放出嚟，跟住我都即刻問佢咁佢咩意思？即係個學生可以唔使影，佢係唔係 OK？佢 OK 我唔使出。講真咁大個人睇佢着黑色鞋都唔大，我覺得佢 OK，我哋少去咁冇問題。但到時我會話點解少咗個？
你有幾 strong 咯？你知你要同埋要事前知喎，你又唔可以。
冇啊！
即係點講咧？即係你就算同佢講話佢着黑色鞋，但係佢都即係會有 argument， 即係佢
都有同佢哋
我自己有啲
都係
即係最好就一開頭就講話你唔着咧，你就唔影，影唔影。
所以咁 upcoming 如果有啲咩都
即係或者講話你可以影，我自己唔影，但係我哋出街嗰張相就冇咗你。
係啊。
影兩個。
upcoming 嗰啲出嘅應該全部都係咁講。
一早知咯，但係因為冇即係我唔知呢個係咪啱啱決定啦。咁但係你要早啲知咯，如果唔係我唔知即係如果我係作為一個
15分
作為一個 admin 或者一個secure嘅人，你要諗埋，喂咁你如果突然之間講呢樣嘢，咁同我哋講 understanding 未必一樣。咁人哋家長可能會嘈你咯。
係啊。係佢哋自己定邊個出 post 㗎？
哦，佢哋知㗎，因為有預備過嘅。
Okay. 4 minutes to.
Okay, so today I'll be opposing the problem of awesome coin. So firstly, this is the statement I will repeat it because it will be repetitive. So we believe that there are 3 tasks to this problem. Firstly, the dynamics of falling coin. Secondly, they should do a parameter analysis on the motion of the coin. So how does like the density or like the initial angle, how does it affect the motion of the coin? Sorry. And then thirdly, I think that they should have done the conditions and boundaries of the regimes of the coin. And we believe that while the first 2 tasks are somewhat complete, the third one is was quite lacking from their presentation. So we believe that the task will be partly completed. So then let's look at the theory. So they firstly explain how the qualitatively there's the pressure asymmetry. So that means that it will create a vortices, and therefore like there will be a talk about the center of the pressure and create the fluttering. However, we would like to point out that the assumption of the 2D is quite unrealistic. While it might be in some cases conservative, while it might not really be actually accurate to assume it. And then they also investigate on the other mass from literature, and also neglected the relief, which we quite agree with that approximation is well known. And then also the literature source constants were fine. However, we would like to stress again that we were not really sure what were the own contributions from the reporter, and we would like to discuss it later. And then for the experiments, there's a lot of coins that was used. So that this like the DET and also the water tanks the water tank's viscosity was also varied, density was varied, and then they used the salt to change density, and also the tracking. They track the coin. However, I'm not really sure how they track the coin, and that will be another point of analysis later. And then for the analysis, they only show the angular velocity and the time it takes to drop down to the bottom. But throughout the presentation, we were not really sure whether they have actually correctly predicted the dynamics of the coin. As in, they should provide a side-by-side analysis of how the CFD and also the actual model aligns. So we believe that will be a good add. And then therefore we believe that the strengths are as follows. So there's some clear regime videos in the beginning of the presentation. The qualitative explanation was very complete as well. And a lot of the atom mass and also the circulation, and also the comparison between the autumn leaf and also also the coin was well done as well. However, there are some points to improve. Firstly, the chaotic mode was not really discussed further, so we don't really know what is a transitional mode means. Because somehow there can be different planes of movement. We'll discuss it later with the opponent as well. And some of the coefficients were fitted, and some of them, and like most of them were from literature. We're not really sure if they have actually verified if the literature constants were actually possible in their simulation, in their experiments. And then the theory, I think it makes the idealistic assumption of 2D again. So therefore, this will be some of the discussion points, and therefore I invite the reporter to come to the stage. Yeah. So firstly, I want to know how did you, for the experiment, how did you track the coins?
So, okay, I can draw it. So I made a video with 1000 FPS, but it's like hard to track. So let's say that I have a point and I hand track the position of the like size of the point.
So
could I comment on this like for?
Did you use the tracker?
Yes, I use tracker.
Okay. So
hand track.
Okay. So you
just.
I'm just thinking about how do you define these
values? So these boundaries are actually for my simulation. So running my simulation for different point diameters, I can look at it.
But the problem is, you said that it's the Lyapunov exponent. So that means that so what I assume if the exponent is positive, is that even in some of the tumbling regions out of this, there will be a transitional phase. That is like it should not be a deterministic line. It should be like a blurred line where both regions should be possible.
Well, what I believe that when I have like the positive Lyapunov exponent, it doesn't change really like the state. It's always like it does still tumble, but maybe the like trajectory itself looks a little bit different because it can like you can imagine it can like fall for a longer time, for example, or go to the different like other side.
Okay. So
like there could be some like even like the boundary. It is really hard to like examine, but for my simulation this works.
Okay, I want to discuss more about the experiment conditions right now.
Okay.
So for the electro method, how do you exactly release it? Does it have an initial angle change? Because as you have shown already, the Lyapunov exponent shows that a small change in the initial conditions will have an exponentially large effect.
Yes, still I would like to comment that my Lyapunov exponent is pretty small, so this does like indicate, like some chaotic behavior, but it's not like doesn't work. But for my initial release conditions, for the graphs that were with my so here I had let's say that I had the electromagnet like on like an angle.
Yeah, okay.
And
so there's an initial angle.
Yes, there's an initial angle, a small initial angle. And this is because that when I have like the aquarium is
so the initial angle, is it tilted in parallel to the camera?
The camera, yes.
Okay, so it's perfectly parallel.
Yes,
I understand.
It should be parallel. And when I have my aquarium like this, if I like just release the coins, like you could see here without the initial angle.
With this have you considered a case in which there can be like initial methods is very sensitive to the initial conditions. So have you observed a case in which you have the same initial conditions but there are two different regions?
Well, I believe that for my experiments, before these are the same initial conditions for my experiments, but I do agree that like from the electromagnet it can be some difference, maybe one side can start to release the angle, the coin like faster than the other, or there can be some like from the experiments before some turbulence in the water or something like small.
So for here I would suggest a reporter to analyze the cases at the boundary of the conditions. Because right now, like there isn't a lot of analysis at the boundary.
I do agree.
And also, as you have shown in your top video, so you can see that it actually moves in the 3D direction. So doesn't. So if it moves, it actually moves in the 3D direction. I would suggest you to actually put a sideways camera here, and then you sync them.
This is what I would like to maybe explain more. So this is why for these experiments, I have it tilted, right?
Yeah.
Because if I have, what the tilting does, it change, it like, I can control to which side it tumbles. So it goes, for example, tumbles. So it goes like
But
perfectly.
you said the initial condition, this is the same initial condition.
No, it's not actually.
Oh, it's not.
This is the initial condition when it is like the electromagnet is completely like straight. And this is with like a large enough initial angle that it always like goes to the right, like the side that I want it to go.
Okay.
Right? So it doesn't like bump into the equator here or some like things happen.
It kind of does, but
Here it does, but I mean in all of these other experiments it doesn't.
And can you go back to slide 10?
Slide 10.
The one with the this one.
Oh.
Sorry.
Sure.
Okay, so as you can observe here, this sideways camera is not really. I don't believe this experimental setup is actually sufficient because, well, can you play the video? Like it's like the plane that it moves is not parallel to your camera.
I believe that assuming that this is 2D motion is still valid.
Yeah, exactly. So that's why I believe that your 2D motion, the 2D assumption that you have used is completely like it's somewhat contradictory to your experimental.
Well, I believe that this is like demonstrational video,
Okay.
but still, like it still like tumbles to the side like. It
So then,
doesn't
what is your justification of using the 2D model instead of the 3D?
Like for example, using the 3D would be extremely complicated. It's like a very complicated problem, and this is why we like simulated even my coin the way that I explained before. But I still believe that it does move like in a plane that you can say that it's like two-dimensional.
And therefore, can you show me if you have done a comparison between like what is the condition of these? As your theory is quite deterministic. Your theory of the 2D case is deterministic. So why do you get the transitional from your theory? How does your theory actually align with it? Because we don't really see
like what we actually from my simulation, I'm able to like plot and like see my I'm able to see the motion from even my like simulation. I'm able to like see how
I
it
don't
goes
see
on.
the agreement. I don't see the agreement between.
I don't have it like side by side completely like simulation and but like this is what you meant? Like how I'm able to say that this is the transitional movement. I define the transitional movement as when it doesn't like completely tumble from the beginning to the like let's
But
say
in this case, do you think that it's possible because there might be different planes of movement. Is it possible that you observe one state in one camera perspective, but in the other camera perspective, it shows the other phase of motion? Do you think it's possible?
Like, I believe that I would be able to like see still in it, like because tumbling is that it like turns, right?
Yeah.
This is how I define tumbling, and fluttering is when you go from side to side. But so I don't believe that this would be different. And, and we can look at from the like top when I release the coin. This is like a demonstrational video, but it goes like straight to the side. You can like it goes straight. So this is why you can assume it is like 2D.
Okay, sure. And then moving on, have you considered the oscillating theories of the fluttering? Did you consider this?
Like I don't have a graph of like the period.
Like because the fluttering is like this, right? So it's like this. So have you considered the oscillating theory? How does it affect? Or did you only just do the average?
I have the average velocities and the and this.
But do you
the
think?
average angle.
But I don't really think that average velocity of the drop is that important. Like is that important in this whole phenomenon. I believe that a better way, like a better way of measuring it is firstly you measure you measure this, and also maybe you can use CFD and compare with the experiments.
Maybe
like how,
I could recommend on the CFD. I'm not sure if this is like clear. this CFD that I showed here
Yeah.
is just made using this like program, but I like made a CFD in it, and this is just so we can like say it is negligible to use
so
the
numerical,
relief.
so
My
the numerical,
simulation is actually like using the equations that I showed because this is used like this uses some like simplified Navier-Stokes. It's like a program.
okay,
This
but,
is just for the assumption that the point is smooth.
but back to the problem, right? So if this,
And this is static, so this
but if consider that your camera is at this angle, and then the fluttering is at this plane. So that means that there's an angle that the plane of movement actually differs from the camera. Do you agree? So that means,
well, it's like it's fluttering like this, and I'm looking at it from the like.
I don't really think so because the initial conditions are so sensitive in a way that you cannot really fluctuate at that exact angle.
Well, if I change the initial conditions, the mode doesn't change, or I wasn't able to observe this.
Okay.
If I change the diameter of the point, the mode does change.
So the mode doesn't change.
The mode changes with if you're trying to find it. The mode does change.
Yeah, I'm very interested. So
with the point diameter.
so the coin diameter increase, it will change from here to here.
Okay, going to have to stop you there by this time. Thank you. We go straight on for the opponent summarising the discussion.
Okay, so we have discussed a lot from the experimental setup and also the theory. We believe that for the experimental setup, while we agree that releasing from the water is a very good initial condition. However, it's the electromagnetic setup is however very sensitive, and we don't really believe that they have actually considered the conditions at the boundary. So maybe I suggest that they should have considered the case at the boundary. So between the fluttering, also the transition movement, and also for the the tumbling as well. And they have not really made a statistical analysis on what the chance that the head or tails actually lands on the bottom. And then also there was not really a clear definition of chaotic movement. And while the I star value actually is remarkably similar, remarkably close to the to an autumn leaf, we felt that the analysis of that could be done deeper. And we also believe that the radial sum should be calculated.
That has to be it. Thank you very much. If we could have both reporter and opponent up, because we move to questions from the reviewer. 3 minutes.
So thank you very much for the report and the discussion. My first question would be to the reporter that you decided you changed the diameter of the coin. Could you do that independently from changing other parameters?
Yes. I changed the coin diameter by buying coins with different.
Was it steel coins or?
Yes.
But that would also change the mass, no?
Well, yes, of course, when you change the diameter, the mass.
Yes. Okay. Then you assume that the coins were smooth and also show that they don't affect the coins, but the mass distribution of those coins, I don't think it's.
I believe it's negligible for what I.
Okay, so you measured also the average velocity. Is there a difference in the time it takes for the coins to fall between tumbling and fluttering?
Well, yes, because the velocity of the falling is different, but it's very
You
small
say it's
difference.
basically almost constant then.
Almost. Roughly. It may differ, but.
Okay, so the tumbling angle when the coin tumbles, what does that depend on? Does that change?
I didn't look at the angle.
Yeah, and for your measurements of the landing positions of the coins, did they hit the edge of the water tank?
Yes, here I'm showing you it a little bit. But this was the largest tank I.
Okay, thank you. And in your simulation, why do the states separate at this exact same point?
I'm not sure what you mean. What do you mean?
Okay.
Could
you go to
slide?
slide 49?
49, of course.
Until question for the opponent, why is the 2D model not appropriate for
Well, we believe that as the water is like is pushed like somewhat sideways, we believe that there should be a 3D movement of the thing to ensure that it's like the theory should be more complete and it creates the following dynamics.
Alright, thank you. So here for the simulation, we can see that they separate at exactly the same point. Why is that?
It's not completely at the exact same point, but yeah, this is just how the movement.
Okay, again, question to the opponent, how will you improve the initial setup and initial conditions?
Well, I believe that they should have actually varied the initial angle with the horizontal, because that will affect the stability and the phenomenon.
Okay. Yeah, thank you very much.
Okay, thank you. You have preparation time?
Okay, so
Okay.
I will start. My name is Knight, and I will be the reviewer for problem number 12 on coin. So the overview of the report first. The reporter investigated fluttering and the tumbling mode and the transitional state for the coins. However, I believe that if the inertia of the coin is very small, or if the Reynolds number would have been very high, she could have measured a steady motion as well, where the coin does not flutter or tumble. For the theory, she used pressure differences and the torque and Newton's second law to describe the motion, and use a 2D simulation with the CFE. And for the setup and experiments, she used a high FPS camera and tracked the motion from one angle, although I agree that tracking the motion from multiple angles could have been a better addition. But the electromagnetic release mechanism is nice. And the parameter dependencies, she varied the diameter most of the time, but I believe that does not only change the diameter, and because the inertia of the coin is very important, the results are not comparable in every case because of that. For the strength, she included the added mass and created a very good simulation, and also measured the landing points of the coins. But I think much more parameters could have been considered, like the material of the coin and the thickness, for example. And the coins weren't, the parameters weren't independently changed, and also the boundaries of the regimes weren't very clear, or could have been investigated more. Now the overview of the opposition. So the speech, I think, was good, since the most important things were touched upon. and the boundary conditions were pointed out. And in the discussion, again, he had very good own opinion and they talked about many important things. And but for possible ways to improve, I think that focusing on the camera was a bit too much, since I don't think that does affect the traveling and motion that much for the coin. And now for the discussion, first they talked about the definition of the boundaries, and the reporter said that these were predicted by the simulation, and the opponent said that they should have been more clearly investigated, and I do agree with that, but it is sometimes hard to do so, and for this I think investigating the motion for a much longer period of time could have made these boundaries more clear, whether for the tumbling modes maybe a chaotic fluttering period could have been investigated. And then the initial release conditions were also touched upon, where I think the electromagnetic release mechanism is good, although I would need some clarification of the reporters, what the reporter would say for why the coin tilted initially if there was no tilt angle at the release, why that small tilt happened, which caused the tumbling. So that was not very clearly explained. And then the 2D assumptions were also a topic that was discussed. And here I think that the 2D assumption is good, although the 3D simulation could have improved to, we could have seen the motion of the coin better, but that's hard to do. But I think that 2D is a fair assumption. And I think a very important thing is also the frequency and the amplitude of the fluttering, which was not measured, as well as the landing spots for these regimes. Since the inertia of the coin really changes the amplitude and the frequency the coin flutters at, which is another very interesting and important parameter to measure. And again, the landing spots for fluttering is completely different as for tumbling. And also the chaotic regime could have been investigated more, what the landing spots are there, and why exactly these boundaries happen. That was not discussed as much. And all in all, thank you for your attention.
So we move on to concluding remarks.
So I would like to thank the opponent and the reviewer for this fight, but I would still like to say or comment that I believe that the 2D motion assumption is valid, because we can see that it goes straight to the side, one side, and we don't see any motion. To the reviewer mentioned that I wasn't able to or I didn't study any steady state. I didn't observe any steady state of the falling of the coin. If I used, for example, honey, maybe I would be able to observe this, but this is really hard to do. Then for the transition between the fluttering and the tumbling, the transitional movement mode is this transitional mode which the opponent talked about. And yeah, I would like to say that I'm not sure if this was clear, but I had the simulation, which is actually dynamic, and then the CFD is for checking the assumption of the smooth point. And with that, I would like to thank everyone for the fist fight.
If I could ask reporter, opponent and reviewer to the front, and we will move on to questions of the jury. Do we have someone who wish to start? By all means.
Yeah, I have a question of the reporters. He referred to some papers where you took those constants, drag constants, for your coin, and if I see correctly, those papers are for cards or something?
Yes, but they had different values, and some of them were for thicker, or
what about
temperature, this is what I'm doing, right? I have the coin, right? I'm not sure how to draw it, and I just take the cross section because it's like two-dimensional.
Yes, but you consider the legible cross sections to say that are they expected broken or
Well, I believe this is still like fine.
Okay.
And or in the papers actually they do like use the like ellipse for the assumptions, because again like modeling 3D card was like hard in the papers, I believe. So they use
Okay, yeah, I got the answer.
Okay. Can anyone else have a question? Maybe come back on that if you want to ask more later. Yep.
To the reporter, in the different mode, you have 3 different modes, right? The tumbling and traditional. And that means there's 2 critical boundaries. What happened at that boundary physically? What changes? What makes that critical boundary?
well, like from my like experimentally I wasn't able to like verify this, but I believe that here
I'm not asking about the verification, I'm just asking what happened there
like the
physically.
like the point diameter changes, and this like affects the like dissipative torque, and it like basically.
So only the point diameter is the critical factor.
And it
that
just
makes
doesn't
the
do the like straight fluttering. It does like something in between. But more to this side, if I could like just like looking from like, my experience, on this side it looked more to the like the tumbling, but it sometimes did something like fluttering, and on this edge it does like mostly fluttering, but it does sometimes something cool.
The question is what makes that? Why that happened right at that point? Why?
Well, yes, because with the changing the coin diameter, like the dissipative torque is different,
Okay.
and it like stops the movement.
Okay,
If this
you're
is
repeating you. Okay, next.
Maybe Nasrina. Yeah, so you calculated this development exponent and you discussed it a lot. Could you please clarify what is the lifetime of your coin?
like
the
how
time of the whole time of the motion.
well, like less than a second.
And you consider it to be like reasonable time for calculation of development exponent?
Well, like the Rosenstein algorithm like takes care of like do you want me to explain how it like calculates it? But because I believe it's like valid to use in this.
Yeah, so you did calculate it experimentally. I'm talking rather about experimental verification. In theory, I understand you can simulate the infinitely large container.
Yes, but in my simulation I used like the height to be, or like the time of the falling to be like similar to my experiment. Like the same as my experiment. Like average. Yes, and it is like the Rosenstein algorithm takes care of these like small data sets. This is
Thank you.
yeah. I can explain how it works, but like
Can I come back to the boundary issue
Yes.
and ask the reviewer and the opponent? You both said that they could have focused on that. What would you have done to focus on the boundary condition? What would you do in your experiment?
Because the point about the boundary is that the initial conditions are very, very sensitive. So that means if you repeat it like 100 times, obviously more is idealistic, right? So if you repeat it, you can get the kind of statistical chance that that it will go to the fluttering regime, or it will be merely an undefined regime in the middle of the transitional movement. So that means everything like in the boundary is probabilistic. Yeah.
Okay, so statistics. Okay.
I would have used more coins if possible to measure these regimes, and also increasing the height of the water tank to observe the motion for a longer period of time could have been important. And I also believe that looking at just the diameter is not sufficient in this case, since the
Okay.
yeah.
Thank you. Good. Oh, okay, no further questions. Thank you very much. Everyone sit down and we will compile marks.